And we are live. Hey everyone, welcome to our night 3 math for our ACT Crams. It's October 25th, nice Wednesday night. And yeah, so I'm Anuva. I'm just going to start off with introductions. I'm a first year at Grinnell College studying biochemistry with concentrations in neuroscience and policy studies, also on the pre-med track. And I'm going to be leading you guys through our content today and like basically the first half of our stream tonight. Dylan, you want to introduce?
Hey everyone, I'm Dylan. I'm a third year history and economics major, math and data science minor at Northeastern up in Boston. I'll be going through the rest of the material tonight and all of your practice. Super excited to be working with y'all tonight.
So let's just get right on started. So we just did our introductions. So make sure to follow at Fiveable on all social media. We got TikTok, Instagram, YouTube, LinkedIn. My personal favorite is Instagram. I'm loving all the like nice little creative posts that we've been having recently regarding majors. So you guys should definitely check those out if you want to stay on top of everything that we're going to be doing. So once again, we are here on a full night for our ACT crowns, but we're just going to say all of the benefits again of cram mode and what you guys are getting. So we got practice questions. So we'll be going through a bunch of practice questions tonight, but then as a part of cram mode, you'll also have access to a bunch of unit specific questions and explanation to test your knowledge on. You got these cram finales like the one that we have tonight, unlimited access to all of the live events days before the big exam. So we have ACT right now, but we also have for APs, SATs, PSATs, and deadlines such as college admissions. We have study guides, cheat sheets, study plans, any exam prep to keep you guys on track, and first access to new features. So you'll be able to see any updates that we're making and all of the new content that we're having for you guys. And my favorite benefit of cram mode, you get to see more of me, Dylan, and a bunch of our other cram co-hosts. So yeah. So here are just a few community agreements before we start tonight. We just want to make sure to be respectful, be supportive, be patient, be kind. We're all real people here, and we're all here to learn. Tonight we're doing math, but just in general, we just want to be able to learn in a safe space. And we have a limited amount of time together, so just be patient if we don't get to your questions. But we'll try to get to as many questions as we can. We have that Q&A feature that's on the side over there, so drop your questions over there or in the chat. And yeah. So here's the agenda we have for tonight. So we just did our welcome. We'll talk about the basics for the ACT math section. We'll talk about preparing for higher mathematics and integrating essential skills, and then we'll wrap up tonight at the very end. We got a nice 2 hours together, so we'll make sure to cover as much as we can. So for the ACT math basics, so this is the format of the ACT math section. So you have 60 minutes to complete 60 questions. So if you do the little bit of math on that, you got 60 seconds per question / 1 minute per question. So how I like to see it is that all of like the ACT math questions aren't the same difficulty. You're going to get more easy ones and you're also going to get more hard ones. So I wouldn't necessarily say like spend exactly 1 minute per question. That's just the average amount of time you have per question. But like, for example, for the easier questions, you're going to spend a little less time on those. And then for the harder questions, such as like the long like essay questions that they give you, where you have to like read a bunch and then answer the question, spend a little bit more time on those. And just because time is so crucial on standardized exams like this, you can bring a watch, timer, or a stopwatch to pace yourself during the exam, but it can't have an alarm. So as long as you have anything that can like keep track of time or that like won't go off, that's fine. And like you can't bring smartwatches just because of cheating. So like if you have like I guess like a digital watch that like doesn't have like an alarm, or even like one of the analog or clocks, like wristwatches. Yeah. So you can bring those. So here's some more details. So we're just breaking it down for you guys based on percentages. So we have the big section of preparing for higher math, and within that section, which takes up 57 to 60% of the ACT math exam portion, we have numbers and quantities, which is 7 to 10%, algebra 12 to 15, functions 12 to 15, geometry 12 to 15, and then statistics and probability, which is 8 to 12. And then we also have integrating and essential skills, which is 40 to 43, and then modeling, which is basically like graphs and stuff that's like in relation to all of the other topics within preparing for higher math and integrating essential skills. So we have a few tips that are on the right-hand side, where it says questions on the ACT get harder as you go on, so the last 10 are the most difficult. So how should I say this? So like what I said before about like the easy questions, you're most likely going to get those in the beginning. You should spend less time on those and then spend more of your time, like the extra time that you have from there, on those last 10 questions. And you can use a calculator on the whole section and just make sure it's approved. There's a whole list of calculators that are approved on the ACT like testing website. And it's not like the SAT where there's like a calculator section and a non-calculator section. This whole entire math section, you can use a calculator. So we're going to start with preparing for higher math. Okay, so just an overview of what's in this section. We got numbers and quantities, algebra and functions. So within numbers and quantities, you're talking about real and complex numbers, negative or fractional exponents, vectors, and matrices. And then in algebra, you're talking about lines, polynomials, exponential and radical relationships, solving systems of equations, using simple matrices, and then you have functions, which is function definition, notation, and representation, manipulating and transforming functions, and finding features on graphs. So I know I said a bunch of words. We're going to break down each one of these in just a little bit. So if you don't know what some of these words mean, totally okay. We're going over that tonight. So, and then to also continue, we have geometry and statistics and probability. Within geometry, we have congruence and similarity, surface area and volume, trigonometric ratios, solving for important values in shapes, which is vertices, the radius, etc. And then we have in statistics and probability, we have describing the center and the spread of distributions, analyzing data collection methods, understanding data relationships, and then calculating probabilities. And just like we have our like little owl friend saying on the side, it's a lot, but we're going to be taking it step by step for you guys tonight. So let's start with numbers and quantities. So here's some properties of rational exponents. So I'm sure you guys have seen rational exponents. So for example, a here is a constant, and then we have, and make sure you know that like a, it's like the same for them. So like for the equations that are being put on there, both of these a's have to be the same so that they're represented by the same variable, as opposed for saying a and b. So the x is the x and the y are the exponents. So then here are some like properties that they have. So we have, if you multiply them together, then you can add the exponents. If you divide one by the other, then you subtract it. If you do a to the x to the y, so like the y is the exponent of the first a to the x function, then you multiply the exponents together. And then if you have, if it's a negative exponent, then it's 1 over and then a to the x. And of course, just anytime this goes throughout the whole stream, if you want me to repeat something or explain it further, just drop it in the chat and I'll go over it once more or more in depth. So we're going to be looking at like what a matrix is. So personally, I didn't really understand what a matrix was until like I was studying for these exams. So totally okay if you guys don't know what a matrix is, because I believe like you don't really go over it in general math. Like totally correct me if I'm wrong. Like for example, like I never went over what a matrix was until I was studying for I took the SAT, for example, but I also took like an ACT. Didn't know it before that. But anyways, a matrix is a rectangular array representation of numbers, variables, or both as rows and columns, and then the order of the matrix is the size of a matrix. So, for example, we have the matrix A, which is a 2 by 2 matrix, and then, for example, there are 2 rows and 2 columns. And then on the other hand, there's B, which is a 2 by 3 matrix, which has 2 rows but 3 columns. We can go on to the next slide. So over here, we are going to be talking about like the multiplication, addition, and subtraction. So for example, we have A, which is listed like on to like the top left. So then, for example, if we wanted to multiply that by 2, so we have 2A, we multiply all the components of the matrix by 2, and then you can see it on the right-hand side what the result of 2A is. And then you can see like when we're adding together two matrices, we have A and then B, which are listed in different colors. And then we're basically like matching them to like the same area of them. So like, for example, like the top left numerical value, you're adding them together. You're not mixing and matching. So you have the A plus B, and then that's written across there. Dylan, correct me if I'm wrong, but I don't believe you need to know like how to like add multiple sizes of matrices together. So like a 2 by 2 and like a 2 by 3.
So yes and no. I say yes because you can't add matrices of different sizes. If you have a 2 by 2 and like a 3 by 3, you can't add them together. Like physically you can't. And so like yes, you should know that you can't do that, but like you don't have to know how to, because there is no way to.
Okay. Yeah, I was like thinking if you could, but thanks for clarifying that.
Because if you're adding corresponding elements of the matrices, by the time you get to like the third row in the 3 by 3, there's no corresponding element in the 2 by 2 and vice versa. And if you just think about it for a little bit, you can realize that your matrices have to be the same size to add. They ask you to add 2 matrices and like you have 4 numerical answers, you can add them together. Like they'll never give you a trick question.
Yeah, like literally I learned matrices for this, and then I haven't used matrices until like multivariable calculus, which is what I'm in now. So like don't stress too much about it. It's a lot simpler than like you need to know like about, I guess you wouldn't need to know the multivariable one. So yeah. So we can go on to the next slide about algebra, I believe. Oh, I just saw a question in the chat. Hold on, let me. Oh, okay, thanks, Dylan. Basically, the question was just asking how would we want to multiply matrices of different sizes, and we wouldn't need to know. We wouldn't need to do a matrix to matrix multiplication on the ACT. So we're going to move on with algebra. So my favorite topic, actually, I don't know if it's my favorite. It's one of my favorites. We're going to start talking about quadratics. so a quadratic is any polynomial of a degree of 2. Its standard form is f of x equals ax squared plus bx plus c, where a, b, and c are constants. However, not all quadratics are in this form. As long as the highest degree is 2, it's a quadratic. And just to answer Marilyn's question, if you're multiplying a matrix just to a number like 2, like a constant, then you multiply each part by 2. So yeah, you are correct on that part. So we have a nice little practice question for you guys over here. So if you just want to drop in the chat, which of the following are quadratic expressions? We have a list of A, B, C, D, and E. And then there can be multiple answers. So, and then while you guys answer that, there are several methods to solve quadratics. We've got graphing, factoring, square roots, completing the square, and the quadratic formula. So you guys should totally drop it in the chat. We've got A so far. We have A, B, D, and E. Anyone want to drop another thing? Okay, so we can go over the correct answer. So definitely A is a quadratic. Remember, we have the a polynomial to the degree of 2. So we have A, where you can see the first term is 3x squared. We have B, and although we don't have like that middle term of B of x, that's still a quadratic just because we have a term that is to the degree of 2. Obviously, it's not C, because even though we have a polynomial to the degree of 2, we also have a polynomial to the degree of 4, and the highest degree is 4, so it's not a quadratic. And then same thing for D, where you can see if you multiply the square out, then the highest degree would be x squared. And then for E, if you FOIL it out, the highest degree would be x squared. Nice. So we can move on to the next slide where we'll start talking about methods to solving quadratics. Okay. So we have factoring quadratics, which is quote unquote undoing the distributive property. So suppose we have like a general quadratic in the form of x squared plus bx plus c. So we can think of this quadratic as like a product of 2 binomials. So we have x plus d, d being a constant, and then f, x plus f, which f is also a constant. So then when you FOIL that out, it becomes x squared plus, and then you want to do like the 2 terms. So those are combined where it is, so we have d times x, and then we also have f times x, and then you can combine those 2 to become d plus f times x. And then we also have df. So to find d and f, we need to find 2 numbers that multiply to c and sum to the letter b. C and b being referencing the form of x squared plus bx plus c. So now we have a little practice question over here that we'll walk you through, where it's x squared minus x minus 20, and then we want to find what a and b are by like undoing the distributive property and factoring the quadratic. So we want to figure out what sums up to -1, because negative x, the constant in front of it, is -1, and then multiplies to -20. So when we're doing this, it's, how should I say this? It's a lot of like guess and check, I find, but you can also look at like what are the factors of the constant of like d times f, or like in this case it would be what, a times b. So for negative 20, you have to think about all of like the factors that go into it. So if you think of factors of 20 that negative 20 that would sum up to negative 1, you can think of the two factors negative 5 and 4. Because if you add those two together, then it becomes negative 1. And then if you multiply them together, then it is negative 20. So in this case, in order to find A and B, you would just, I like to use guess and check when factoring easy quadratics like this, but there are also different ways for more complicated quadratics. So in this case, it would be x minus 4 plus, times x minus 5 times x plus 4. So yeah, so we can go through all of these, and there it says at the bottom, x minus 5 times x plus 4. Or it could be x plus 4 times x minus 5. That order doesn't matter. Go on to the next slide. So here is a fan favorite of completing the square. I personally don't like completing the square, but I know a lot of people who do. So with completing the square, when the coefficient of the linear term b is even, completing the square is always a good option. It's always possible to complete the square, but when you have like odd coefficients, it's not always fun to do so. So after we complete the square, we can solve by square roots, and when we have circles, completing the square will also become handy. So we're going to break down the steps for you into 3 simple pieces. So we have the first step where we divide by a and subtract by c from both sides. We calculate b over 2 to the power of 2, and then add it to both sides, so then the left side becomes a perfect square. And then we take the square root of both sides and solve the equation. So we're going to walk through how to complete the square on the next slide. So here's a nice example where we have x squared minus 6x plus 8. So first we're going to move the constant c onto the other side of the equation. And then we have x squared minus 6x equals negative 8. And then we want to add the negative b over 2 to the power of 2, like little expression to both sides to form a perfect square trinomial. So negative 6 over 2 squared equals 9. So now we're adding that both. So then we have x squared minus 6x plus 9 equals 1. And then we have the nice little x minus 3 squared equals 1. And then you can take the square root of both sides and then solve x. And then we get x equals 2 and 4. So it's really friendly when we have an even b coefficient, but when it becomes odd, then it gets really complicated for when you divide it by 2 and then square it, and then you get some really ugly numbers. So it's a good option if you have an even b coefficient, but if not, maybe doing a different way, such as the quadratic equation might be, or quadratic formula might be a little bit better, which we will talk about next. So we have the quadratic formula, personal favorite, of x equals b plus or minus the square root of b squared minus 4ac all over 2a. And we're taking these constants from the equation of f of x equals a squared plus bx plus c. So why might you do this? But if you have done this in your class or you haven't, the quadratic formula is actually what it would look like if you took the standard form of the quadratic equation and you solve for x. So it's a nice way to save time if you have like a really really like complicated equation, and you can't do guess and check like we did before, or you can't complete the square. Quadratic formula always works. Might look complicated, but it always works. Plug it into your calculator, and yeah. So next slide, we're going to talk about graphs. So we're going to go through the steps of matching the quadratic equations with their graphs. So first we're going to look at the coefficient of x squared. If it's positive, the parabola opens upward, so like a nice little smiley face, and the vertex is at the lowest point. So if it's going to be like, oh, I guess I should do like this. So it's like you have like a little smile, and then the vertex is like right here. But then if it's negative, the parabola opens downward, so like a frowning face. I guess I could do it like this. And then the vertex is at its highest point. So you want to find the vertex coordinates using the formula. So we have a handy formula over here where it's negative b over 2a, and then you have the 4ac minus b squared all over 4a. So you don't really have to memorize those. I mean, it's definitely going to help you just to memorize those, and you don't have that equation like on an equation sheet, but it's like worth memorizing. But if you don't, it happens. I believe there's like some other ways you can calculate using it. Like for example, if you put it into your calculator and you graph it out, you can look at the vertex. But yeah, and then you can find the axis of symmetry, which is the vertical line going through the vertex. You find the x-intercepts by solving the quadratic equation where you set y equals 0, and then you solve for the values of x, and then you can draw the parabola from there. So like, for example, like on the ACT, you might have like a question that like gives you the equation, and then it is like, well, which one of these graphs match to that equation? So you might have to do something like that. But you won't have to draw it out, but you need to know how to match the equation to the graph. Go on to the next slide. We're going to talk about some exponential equations. So we're going to look at the purple one first, where it's a type of growth whose rate of increase becomes faster over time, proportional to itself. So the equation for this would be f of x equals a, which is a constant, 1 plus r to the power of x. And then one that decreases faster over time is f of x equals a, 1 minus r to the power, to the power of x. So that's how those two graphs look like. It's a exponential equation. Not sure if you've seen like one of the more commonly used ones is like e to the x, something similar to that. Like the shape of the graph is like very similar to that. Go on to the next slide. And then if we set it up like a system of equations using x equals 0 and x equals 1, the corresponding y values for x and f of x. So for example, if you like look at the equation, so anytime you set something to the power of 0, you get 1. And for example, how should I say it? Like the constant a in the front is like the most useful for identifying where the graph is at x equals 0. So that is technically like the y-intercept. And then you can, and then once you get x equals 1, you can plug that in to set it up like a system of equations. So here's some quick, okay, so here's some quick exponent rules. We went over a few of these within like the last little unit thing, but we have let's so we went over the first 3, and so for the fourth one, where you have a times b to the power of x, you can distribute that out to have a to the x times b to the x, and then you also have what I just said earlier, anything to the exponent of 0 equals 1. And then we talked about x to the power of negative a, which equals 1 over x to the power a. And then we have the last one where it's x to the power of 1 over a, and that's the 8th roots of x. Oh my god, I can't even stop talk. But yeah. So yeah. Okay. So now we'll talk about systems of equations. So we're going to do a little bit practice with this. So the 2 steps for this is to isolate either x or y by multiplying the equation by a factor that cancels the x or y. And we are going to use PEMDAS to isolate for y and plug y back into the equation to find x. So we're going to give you a minute for this, and then we're going to go over how to do it just in case you guys are having trouble with it. So yeah. Okay, so I hope you guys were able to solve the question, but if not, no worries. We'll go over it right now. So you could just do the entire slide and then I'll just go through it. Yeah. So we have negative 2 x plus y equals negative 2 times 3. So if you look at that, then the x plus y, essentially, if you multiply it by negative 2, then it will match. So if you can see over there, the negative 2 and the 2x, if you add them together, then they'll cancel out each other. So what we're doing here is we're going to add the 2 equations together. So you have on the third part, the third blue and purple lines before we mix the 2 equations together, we have negative 2y equals negative 6, and then negative y equals 4 after we cancel out those, and then you combine those together to have negative 3y equals negative 2. So now we isolate y, so we divide each side by negative 3 to get y equals 2 over 3, and then we're going to plug it into the first equation where we're replacing y for 2 over 3, and then we'll have x plus 2 over 3 equals 3, and then x equals 7 over 3. So that's how you do it. If you guys need any clarification, just pop it in the chat. But yeah, it's really not that hard. Pretty simple once you break it down into the steps. So we'll start talking about solutions of systems of equations. So when we're looking at the graph, each of these graphs are different when you're so here, Dylan, can you move back one step? So just so we can clarify this. One slide, sorry. So the negative 2, so you're manipulating the first equation to be able to satisfy crossing out the x, so getting rid of one variable. So the -2 comes from like us manipulating that first equation, because essentially like -2x minus 2y equals -6 is the same thing as x plus y time equals 3, because we're multiplying a constant -2 on both sides. So I hope that helps. We ourselves are manipulating it. It's not coming from like anywhere, but we're manipulating it so we can essentially take out that variable to make it like a one variable equation. Okay, we can move on to the next slide about the graphs. So when we're looking at the graphs, if we have like a system's equations with no solution, they're never going to intersect. So which makes sense, because if it has like one solution, for example, they intersect at one point, and then at that point, that's your solution. But if they're never going to intersect, then they become parallel lines and there's no solution. For one solution, as I said before, they intersect at one point, and then indefinitely many solutions is when the lines are the same exact line. So we're going to go through another question of systems of linear equations with a graph. So basically, I don't know if yeah. So we're going to be taking a look at the systems of equations that we have right here. We have 3 of them, where you have x minus y is less than 2, x is less than or equal to 3, and then 2x plus y is less than or equal to 4. And then we want to graph these out. So if you guys like have like a little notepad or something, yeah. And then we simplified it for you by isolating a variable on one side. So we can start with the minute timer. Okay, so we move on to the next slide. So over here, we like graphed all of like the lines. So we have x is greater than or equal to 3. We have x, 2x plus y is less than or, sorry, I totally said that wrong. X is less than or greater, oh my gosh. X is less than or equal to 3. And then we have 2x plus y is less than or equal to 4. And then we have x minus y is less than 2. So then we graph them like it's just an equal sign, and then we start shading in like all of the area that applies to the inequality by using the inequality. So like, for example, like we use all of the solutions that are for the x is less than or equal to 3. Basically, we look at all of the solutions to the left of that because they're less than 3. So when we shade all of these areas, you can see like the overlapping region in like the bottom, like the bottom area where it's like where the label for x minus y is less than 2. So yeah, like over there, that's where your solution is going to be for that satisfies all three inequalities. Cool. And now we have our next section, functions and geometry. Okay, so we have two different types of sequences. We have geometric and arithmetic sequences. So for an arithmetic sequence, to get a term, you have to add a fixed number, also called the common difference, d, to the previous term. And the general formula for this nth term of an arithmetic sequence is a, like the nth term of a, equals the first term of a plus the amount of terms minus 1 times d, the common difference. So this is like, this can be applied to like when you have like, I guess like a set of like a sequence that is being like the difference is the exact same. So like you're adding the same amount or you're subtracting the same amount to the previous term. And then, for example, the question will be like, what would the 87th term in the sequence look like? And obviously you're not going to like add it 87 times. So using that equation, you'd be able to figure that out. On the other hand, we have a geometric sequence, which is a sequence in which each term after the first one is found by multiplying the preceding term by a constant number, also known as a common ratio. So this is like when you have like 1, 2, 4, 8, and then it's like increasing by a certain amount or like a ratio. That's why it's called the common ratio instead of a common difference. The formula for this is the nth term of a equals the first term of a multiplied by the ratio to the power of the amount of terms minus 1. That's a mouthful. Okay, so now we're going to be looking at circles. So what to know? We want to know the definition of diameter and the radius. We want to learn the formula for the circumference given by 2 pi r, or pi times the diameter, and the formula for the area given by pi r squared, and knowing what the fraction of the circle the sector is. So yeah, so the ACT does not provide any of these formulas, so it's make sure to have these memorized. But so for example, like the diameter is like, we have this really nice graph over here. It's like from one end of the circle to the other end that cuts across through like the center. And then the radius is half of that. So like, for example, like one end of the circle to the center of the circle, that's the radius. And then a sector is like an area of the circle. And then we just went over what the circumference formula for the circumference is and the formula for the area is. So now we'll go on to triangles. Nice geometry. We have the nice trigonometric functions of sine, cosine, tangent, cosecant, secant, and cotangent. So we have the funny saying that I always memorize of SOHCAHTOA, where SOH, which equals sine equals opposite over hypotenuse. We have cosine, which is ka, which is CAH, which is cosine equals adjacent over hypotenuse. And we have TOA, which is tangent equals opposite over adjacent. So for example, let's put this into perspective when we're talking about like one of the points. So like we'll take x. I just realized it's gonna be a little bit confusing, but okay, so the sine of x is lowercase x, which is the opposite, over the hypotenuse, which is z. lowercase z. For cosine, it is the adjacent, which is lowercase y, over the hypotenuse, which is z. And then we have tangent, which is opposite over adjacent, so we have lowercase x over lowercase y. So we also have cosecant, secant, and cotangent, which cosecant is the opposite of sine, so it's like the inverse of it, so it is basically sine but flipped, so it's hypotenuse over opposite. We have secant, which is the inverse of cosine, which is hypotenuse over adjacent, and then we have cotangent, which is the inverse of tangent, where it's adjacent over opposite. So putting this into perspective of our angle x again, the cosecant of angle x would be the hypotenuse over the opposite, which is lowercase z over lowercase x. Secant, which is the hypotenuse over adjacent, that would be the lowercase z over lowercase y. And then we have cotangent, which is the adjacent over opposite, which is lowercase y over lowercase x. And then we have like the little, I guess, how should I say it? Like the contractions of them, which is like sine, sin, cos, tan, and then cosecant and all of that. Move on. The question in the chat, we have SOHCAHTOA, but is there something to help remember the reciprocals? I mean, for me, I personally don't know if there is one, but like how I just remember it is that, so sine, yeah, so it's just the inverse of all of them. It might be a little bit confusing with the name, but like with practice, you'll be able to figure out that like, oh, cosecant is with sine, cosine is with secant, and yeah. Move on. So we have some extra formulas of, so we have sine of A, the angle, over its corresponding, or I guess like its opposite side. It equals sine of B over the opposite side, sine of C, opposite side. So then those equations can be set to one another and are equal to each other. And then we have sine squared theta plus cosine squared theta equals 1. And so cosine theta, so it's the angle opposite to the opposite side. So like you have, how should I put this? Like if you were to take theta and then you take the sine squared, it's not sine of theta plus cosine of theta. You have to make sure to keep the square. It can equal 1, and then you can rearrange that formula. So for example, if they're asking you like, if they're asking you of like, they'll give you like sine squared theta equals 1 minus cosine squared theta. You can like rearrange the formula to equal certain values. But yeah, that's just an algebra concept of that. But those two formulas are nice to memorize. Sometimes you have like tricky questions on the ACT about that. But okay, so now we have statistics and probability. So we want to estimate using sample populations. So a sample proportion times the population equals the estimate. So we have a nice like question we have over here of 50 seniors at a particular high school are randomly selected for a survey. 21 of them report riding their bikes to school at least once a week. If there are 300 seniors at this high school, what is the reasonable estimate of the total number of seniors? Oh my gosh, that scared me. I got a notification on my computer. Of a total number of seniors who ride their bikes to school at least once a week. So the proportion, we like using ratios or fractions. So we have the sample proportion over here of 21 over 50. So we have 21 over 50, and then we have the population, which we're trying to estimate for, of 300. So we have the fraction of 21 over 50, and we multiply it by 300 to get the estimated, like the extrapolated data point of how many seniors ride their bike to school at least once a week. So maybe we can reveal the answer on this one. Yeah, so there's your fraction over there where it's 21 over 50 times 300, which is 126. So now we can talk about margin of error. So the range equals the estimate plus or minus the margin of error. So for example, if we estimated that 75% of students use Fiveable with a margin of error of 5%, it means we're reasonably sure that 75% plus or minus 5, or 70 to 80% of students use Fiveable. So how should I say this? So when you're estimating something, you're never 100% confident that it is specifically that number, or it is going to be that data point, or in this case, that percent. We use the margin of error to essentially like negate this possibility of, so we have a range of where it could be in. So that goes on to this tip of there is never 100% certainty, and if an answer contains the phrases similar to like we're 100% confident, it's probably incorrect, because there's no way you can be like 100% confident in it. That's why we have margin of error, and you can see this within the math section, but you can also see this in the science section. Okay. So we're going to talk about the center, spread, and shape of distributions. So we got 5 nice little things to describe our distribution. We have the mean, median, mode, range, and standard deviation. So the mean is the average value of the data set, and the mean equals the sum of values over the number of values. So if you had like 5 different test scores, you would add those values of test scores together, divided by 5, and that would be the average test score. For the range, it would measure the total spread. So the range equals the maximum minus the minimum. So again, if we have that example of the test scores, it would be the highest score minus the lowest score to find the total spread of that. We have the median, which is the middle value of the data order from least to greatest. Don't confuse this with the mean. It's not the average, but it's the middle value. So like, for example, it would negate like an outlier, while a mean would take in the outlier. We have, so if it's an odd, then you take the middle value. But if it's like an even, so if you had 6 test scores, you would take the average of the 2 middle numbers to find the median. The mode is the value that appears the most frequently in the data set. So sometimes you can have multiple modes, but then also you can have none if each of the values are unique to one another. And then we also have standard deviation, which is the average distance between the mean and a value within the data set. And the ACT only tests conceptual understanding of the standard deviation, just because calculating a standard deviation can get a little bit complicated. But yeah. So we're going to have a little example problem with standard deviation. I'm going to give you a minute for this. So which of the following correctly compares the standard deviation of the 2 graphs? So you guys can just either pop that in the chat, or actually you can create a nice little poll. That will be up in just a second. Okay. So just pop your answers right in there. So, with this example problem, let's see. So we have 4 votes for A, so we can reveal the answer. So you guys are correct. The standard deviation of the first one is smaller, and that is because the data points are more closer together as compared to B, where the standard deviation is like more spread out just because the standard deviation is bigger because the data points are more spread out. So yeah. So now we'll be talking about probability. Dylan, I think it's your time to take over.
All right.
Our math genius.
You're the math genius.
Yeah.
I'm gonna have to get myself down. All right. Before I jump in, can everyone hear me, see me? I just want to make sure all that technology is working on my end. So just drop something in the chat if you can hear me and see me. And then we'll start talking about probability. All right. I'm super excited. I'm a data science minor. I love probability and statistics, so this is my jam. All right. So let's start talking about probability and statistics, right? Or you talked about statistics. Let's talk about probability. So probability, right, is all about figuring out kind of how likely an event is, right? We have a certain number of events in what we call a sample space, and we want a certain subset of that sample space to happen. So the big question is, how do we figure out the probability of an event, right? So we use a formula. The probability of an event is the number of desired outcomes. So that might be the number of ways to flip heads on a coin, the number of ways to roll a 3 or a 4 on a die, right? The number of ways we can do what we want to do over the number of outcomes, period. So for example, if I am flipping a coin and I say, what is the probability of getting heads, right? Well, there's one way to get heads, right? You flip heads. But there are 2 things that can happen. I can flip heads or I can flip tails. So the probability is 1 over 2, or 1/2. The same applies to, let's say I was rolling a die, and I wanted to say, what's the probability of me getting a 3? Well, there's one way for me to roll a 3. I roll a 3. But there's 6 total outcomes. So that n of A is 6. So the probability is 1 over 6. This is usually kind of your holy grail of probability. If you can count the ways there are to do something and the number of things you have, probability is just a simple ratio. The probability of something not occurring might seem a little more confusing, but actually it's just 1 minus the probability of something occurring. And the way we can kind of think about this is something either happens or it doesn't, right? That's like either something will happen or it won't happen. So either of those things will definitely happen. That's what this 1 is. Right, that's the probability of something happening. Now take away all the cases where x occurs. So everything minus x occurring is x not occurring. So that's something to keep in mind. In general, this is kind of a nice trick where if you have trouble figuring out the probability of x itself, you can sometimes figure out the probability of x not occurring and then subtract 1 because they always add to 1. So let's look at an example. Suppose you have a large popcorn bowl with colored discs. I don't know why it's a popcorn bowl. A large bowl, right? A lot of the time we call them urns in probability for some reason. But a large bowl with colored discs. If there are 15 red discs, 30 blue discs, and 12 yellow discs, what is the probability of picking a blue disc? So let's take a look. All right. So actually, I'm going to give you guys a few seconds just to think through this. Probably not like a full minute, but just like 30 seconds or so while I kind of talk through this. Just to think about kind of how you would approach this, right? We have this formula here. We want to figure out how many ways are there to pick a blue disk, how many ways are there to pick a disk, and then figuring out the probability. So there you go. The probability is going to be the number of ways we can pick a blue disk. So there are 30 ways, right? There are 30 disks, and there are 57 total disks for us to pick from. So 30 over 57 is our probability. We can write this in a number of ways. We can write it as 30 over 57. We can write it as 0.526. We can write it as 52.6%. Those are the 3 big ways, you're going to see it on the ACT. Something to note, that kind of should make intuitive sense. A probability will always be bounded between 0 and 1, right? Because something can't have less than 0 probability of happening. You can't have a negative chance of something happening. And likewise, something can't have a 110% chance of happening, right? It can't be less than definitely not happening, and it can't be more than definitely happening. So, for example, if you're working on a probability question and you keep getting an answer that's like 140%, odds are it's not going to be an answer choice, but you should know that there's something wrong right away, and you shouldn't even kind of validate that answer in your mind. But if you get an answer like 63%, that's a valid probability. So something to keep in mind as you think through these questions, just as like a sanity check. So does that make sense? I know I went through that kind of quickly, but I think we've all seen a lot of examples of this in the wild, to the point where I don't have to like hammer it in. And it makes kind of an intuitive sense. But if you guys have any questions, feel free to drop them in the chat, and I'll be here to talk through them. So we've talked about how we can find the probability of x happening, but how do we find the probability of x or y happening? So for example, let's say I am flipping a coin, right? You can't see it, but I'm flipping a coin right here, and I'm rolling a die. What is the probability that I either flip heads or I roll a 3? So let's think about what this means kind of intuitively first. If I flip heads and roll a 4, that counts. If I flip tails and roll a 3, that counts. So they don't both have to happen, just one of them has to happen. The case where both happens also counts, but the case where one or the other happens but the other doesn't also counts in an or, right? Because it's x or y, not x and y. So we have a formula, right? So for mutually exclusive events, mutually exclusive, we'll explain what that means in a second. For mutually exclusive events, x and y, so for example, flipping a coin and rolling a die, the probability of x or y is p of x plus p of y, and we know how to calculate these. So mutually exclusive means, another word for that is disjoint, and what that means is only one or the other can occur. So for example, my example of flipping a coin and rolling a die are not mutually exclusive because both can happen. It's kind of hard to think of truly mutually exclusive events. But in the case that you don't have disjoint events, you want to add this minus x and y example right here, because the logic is we're double counting in doing this. And you can kind of think of that through a Venn diagram. I'm not going to, unless you guys really want me to, in which case I won't like prove that out to you because you won't need it on the ACT. But if you have x or y, you're going to add these two together. So it looks like actually, yeah, so it looks like this example isn't actually the greatest because it does have an and in it. Like it does, these are not mutually exclusive. So I'm actually just going to go through it quite quickly. But so for example, let's say, and there's one reason I'm going to go through it quickly instead of skipping it all together. So let's say we are flipping a coin and rolling a die like before. What is the probability of flipping heads or rolling a 5 or higher? So rolling a 5 or a 6. So we have two events either happening, right? We have the probability of the coin flip, which is 0.5, and now the probability of the dice being greater than or equal to 5. Well, we know, you may be thinking, well, how do I figure that out? Well, how many ways are there to roll a die more than 5? There's 5, or at least 5. 5 and 6. So that's 2 ways divided by 6 total ways, and that's 0.3, or 0.3 is repeating. So those are our two individual probabilities. In the case that we didn't have, in the case that our events were mutually exclusive, which on the ACT they always will be, you can add these two together to get the probability of x or y. In this case, there's a probability of x and y happening that we calculate here, but you can ignore kind of everything on this side, under here. But these are kind of, the only reason I really wanted to go through this was to talk about kind of a situation where you have the variable kind of greater than or equal to or less than or equal to a number. It really just means that you have more cases to consider than just the one success case. Okay, so let's talk about and again, if you guys have any questions on the statistics and probability, happy to talk through it. If you're not quite getting it, don't freak out. It is certainly not the biggest piece of the ACT. I'd much rather you understand algebra more than probability, but it will be on your exam to an extent. So just be comfortable with the idea of calculating probabilities. So let's talk about integrating essential skills. So this is kind of an interesting section, right? it doesn't really have much actual like concrete content. It's more about taking all the content that we've learned so far and bringing it together, right? We've talked about geometry, we've talked about algebra, we've talked about types of functions. All these things are interconnected, right? You're not just going to go, oh, this is a quadratic problem. Here's the problem. Sometimes they'll give you a situation where you need to integrate these essential skills. For example, there's a lot of geometry problems that also have a fair amount of algebra baked into them. There are a lot of algebra problems that might have a couple different types of algebra baked in, right? You might have to use some exponent rules, some quadratics, some factoring. So it's really about understanding how all these concepts work together. So that can involve interpreting a graph. It can involve solving a word problem. In statistics, you can talk about like outcomes and best fit. A lot of the times, these are kind of questions that are probably towards the end of the exam. They're a lot more about making sure you understand how this content works together compared to understanding how one type of problem works. Like, for example, a problem like this will not be, what are the roots of this quadratic, right? That's not an integrated essential skills. But they might give you, for example, a diagram of a bunch of lines and angles that are all labeled with x, 3x, 5x. Now you have to use both your geometry knowledge and your algebra knowledge to actually figure out, what the angles are, for example. All right, so really the rest of this stream is going to be a bunch of practice and a bunch of Q&A, right? Working on what you guys want to work on. I know there was one thing that, let me look. There were two things y'all wanted to hear about first, and I want to make sure we talk about that before jumping into practice. I think someone asked about matrices. Let me find that. Yes, so someone wanted to talk about matrix multiplication and Venn diagrams. I think I'm going to sneeze. I'm not going to sneeze. Okay, so I want to make sure that gets covered first because you already asked about it before we jump into the practice. So I'm going to pull some stuff up right now just to have kind of a visual of what we do. Give me one quick second. I'm kind of pulling this up on the fly. There we go. Okay, so let's talk about matrix multiplication. There is a decent chance you might not see this on your exam, but apparently some people have seen it, so let's go over it. So some notes. There are only certain types of matrices you can multiply, and we'll talk about kind of what those qualifications are. But first, let's just talk about how you multiply two matrices, right? We've talked about how to multiply a matrix by a scalar, right, like a number. But how do we multiply a matrix by another matrix? I could go into a lot of like the reasoning behind why all it works this way. The problem with matrices in the ACT is that a lot of the like intuition is baked into linear algebra, which you don't learn in high school. You learn it in college, and so a lot of it is kind of algorithmic. So it feels like you have to memorize a bunch of stuff, right? You see all these numbers here. You're like, what the heck's going on over here? For matrix multiplication, I'm going to give you kind of a quick and easy trick, right? You have two matrices, right? In this case, A and B, and we're multiplying them. What you're going to do is you're going to take your first matrix, leave it where it is. Your second matrix, almost imagine it moving up to like here so that you have an empty space where B is right now, right? I can't really do that visually, but you'll see why this is useful in a second. What you're going to do is you're going to take each row of A and perform what's called the dot product with each column of B. So what the dot product means is it's just taking each element of these rows and columns and multiplying and adding them together. So for example, the dot product of A and B and E and G is A times E plus B times G. So when we take each row and dot product it with each column, we get AB dot EG right here, AB and FH, that's here, CD and EG, that's here, and CD and FH, and that's here. So that might seem kind of confusing, but when you move this up here, actually, I'm going to try to pull up an online whiteboard, see if I can kind of pull this up in real time. This might seem a little like frazzled, that's because I didn't have anything prepared. But again, if you guys have any questions, feel free to kind of ask clarifying questions in the chat. So let's share this slide instead. There we go. Okay, so we've got 2 copies of this. I'm going to just, oh, I can't, I can crop, okay. So I'm going to crop this to be just B. Let me crop you. There we go. And then I'm going to quickly grab and just kind of get rid of this. This is true art right here, ladies and gentlemen. You are witnessing greatness. Okay. And you can ignore everything over here and here, right? Okay. So actually, let me zoom in a bit. Okay. So the reason I like to do this is because what we can do is now we can visualize these dot products, not like, oh, well, each row and each column, what am I supposed to do? Where does everything go? Take each row and draw a line like this. Take each column, draw a line like that. And where each of these lines intersect, that is going to be a number in your new matrix, right? So here, 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 and here. Each of these points is determined by 2 of these lines. Those are the 2 like pieces that you product together. So for example, we take this row and this column, that's going to be this entry, and we do the dot product, right? Just like before, we said that is going to be AE plus BG, right? Because A, E, B, G. Next, we go to the next column. Well, we have AB and FH. So AF plus BH. Right? Again, it's a pairwise element product. Next, we have the bottom row, CD times EG. So CE plus DG. And then CD and FH, CF plus DH, and you've got your matrix product. So that's kind of a really nice way. And it's actually, I did this on my midterm 2 days ago. I do this all the time when I'm multiplying matrices because it just makes sense, right? You take each piece, right? Like I feel like a lot of people think I have to memorize this giant thing. You don't, because actually what's happening down here makes a decent amount of sense. So let's think about kind of when you can multiply matrices together. So if we have 2 matrices, let's say A and B, right? We need the lengths of each of these to be equal, right? We need the number of elements here to be equal to the number of elements here. Otherwise, we can't do a dot product because each element here has to be multiplied by an element here. So let's suppose A has m columns, or m rows, and n columns. And the same applies here, right? Now let's suppose we have m columns and n rows, right? In this case, they're equal, they're 2, but you can multiply rectangular matrices. What has to be true is that these 2 numbers have to be the same. So for example, I can have, you can see my handwriting coming right here. Let's suppose I have a matrix like 1, 2, 3, 4, 5. This isn't much better than my real handwriting, right? Well, now we know that we're going to have some matrix here that's going to be like our result, our product. So 1, 2, 3 is going to have to multiply by something with 3 elements. Let's say it's 7, 8, 9. Right? We know this has to have 3 elements because it has to match here. Likewise, this has to have 3 elements here. So for example, 10, 11, 12. Right? So you can multiply 2 matrices with opposite dimensions, right? This is a 2 by 3 matrix, and this is a 3 by 2 matrix right here. What we can also do is multiply this by a 3 by whatever matrix, right? I can keep adding. There we go. Is there an eraser? There is. Ooh, that's awesome. So we can keep adding columns as long as we want, right? I can add 50 columns here if I wanted to, because all I would be doing then, right? Let's say we have, a column here, a column here, a column here. So now this is a 3 by 5 instead of a 3 by 2. Well, you can see pretty clearly that we can multiply this, right? If we draw our lines like before, it all works out, right? Because we're going to have 3 elements in each of those columns that can multiply with each of these rows. So that's how you do kind of general matrix multiplication. Something to note, right? So we have a 2 by 3 matrix here. In fact, let's say actually n by m matrix, so 2 by 3, n by m, multiplied by, we now know this has to be an m, right? Because the number of columns has to equal the number of rows, by, let's call this q. The resulting vector or matrix will be n by q, because each of these rows, each of these n rows will become a row in our result, and each of these q columns will become a column in our result. So for example, a 2 by 3 times a 3 by 5, we can see, becomes a 2 by 5. So that's kind of the basics of matrix multiplication. As long as you understand what we did here, that's the important piece, right? And how to apply that over here with like just rectangular matrices. It is not a memorization process, right? It is a quite clear process, actually. And when you take, or if you take linear algebra in college, you'll see actually that this is a whole new world of things. So something to keep your mind open about as you learn more math. If you have any questions about that, I'm happy to talk a bit more about this, but I know we have other things to practice. I'm going to check real quick if we have a Venn diagram question in here just to see. It doesn't look like we do. I'm going to let us do a few practice questions and then do a Venn diagram question, just because some practice will be useful. So let me share the slides again. Awesome. Okay, so let's do some practice, right? We're going to be practicing pretty much everything we worked on tonight. All right. So first question is about arithmetic sequences. What is the sum of the first 4 terms of an arithmetic sequence in which the 6th term is 8 and the 10th term is 13? So before we start the timer, think about what the definition of an arithmetic sequence is and what we can deduce from knowing this about the 6th and 10th terms. If it helps, write out the list of terms with like dashes where you don't know what the terms are. All right, starting now. All right, let's take a look at the answer. So the answer here was 14.5. Right, so let's talk about how we do this problem because it's a bit of a mental kind of game. Right, so we have an arithmetic sequence. First, remind yourself, what is an arithmetic sequence? Well, an arithmetic sequence is a sequence of numbers which each number has a common difference, right? So that is kind of the key number that we want to figure out. In fact, I'm going to write this out for you guys because it may be useful to see this done. Because this is a bit of a tricky problem. I won't do this for all the problems, but this problem especially, just a little tricky. to think through. Okay. So what is the sum of the first 4 terms of an arithmetic sequence in which the 6th term is 8 and the 10th term is 13? Okay. So we're concerned with 10 terms, right? 1, 2, 3, 4, 5, 6 is 8. 7. Wait, how do I make this longer? There we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we do know what these are. Let's call the common difference D, right, per difference. This is 8 plus D. This is 8 plus 2D. This is 8 plus 3D. And 13 is 8 plus 4D. So we know that 8 plus 4D is 13, which solving that we get 4D equals 5, which tells us that D is 5 over 4, which is 1.25. Beautiful. That is the key thing here. From here, we can work backwards. Well, this is 8 minus D, right? Because some number plus D equals 8. This is 8 minus 2D. You'd say the answer was 14.5? Oh, the sum of the first 4. Okay. Whew, I was like, okay. 8 minus 3D, 8 minus 4D, and 8 minus 5D. Right, if that doesn't make sense, let me know. I'm happy to kind of talk through how we got there. So now we want to figure out the sum of these first 4 terms. So 1, 2, 3, 4. We want to add these together. So this is going to be 32 minus 5, 9, 12, 14D is equal to 32 minus 14 times 1.25. So 32 minus 14 times 1.25 gets us 14.5. So that's kind of something to think about when you're doing this problem is first to kind of figure out what you're dealing with, make a game plan, and then solve. Right? So here, the big kind of crux was finding our common difference. From there, we had every element in terms of that common difference by working backwards. Okay. Let's move on. Okay, the expression 3x minus 4y squared times 3x plus 4y squared is equivalent to one of those 4 answers. Minute on the clock. All right, let's see what the answer to this question is. And again, if you have any questions, feel free to ask in the chat. Okay, so the key to this problem is really it's twofold. One, you could FOIL this whole thing out, or you could realize this is a difference of squares. So the answer is A, right? In this case, if we FOIL it, we get 3x times 3x, that's 9x squared, plus 4y squared times 3x, minus 4y squared times 3x. So those cancel out, and then we get minus 16y squared, or to the 4th. So you could have FOILed it out, or you could have realized a minus b times a plus b. Where have I seen that before? That's a difference of squares. So we know this is going to be 3x squared, 9x squared, minus 4y squared, 16y to the 4th. Or 4y squared squared, that's 16y to the 4th. So you could have used one of those two methods to figure out what the answer was here. It's a difference of squares, or it's a FOIL problem. Either way, you would get the same exact answer. If you guys have any questions about that, feel free to ask. Otherwise, we'll move on. For what value of a would the following system have an infinite number of solutions? Minute on the clock. Time is up. So something to realize with this question, which is kind of important, is that you kind of can see a bit of like symmetry here, where 2x minus 3 and 6x minus 3y, or 2x minus y and 6x minus 3y, these are multiples of each other, right? This is simply 3 times this. That's kind of going to come in handy later. Just going to throw it out there. We'll need it later. So what does it mean for a system to have an infinite number of solutions, right? Ponder that for a second. If we have an infinite number of solutions, that means the line defined by this equation right here is exactly the same. I can't do this with my arms. Is exactly the same as the line formed by the other equation, right? Every single xy pair that satisfies one satisfies the other. There are infinitely many solutions. So we have some line here, right? It would be, I guess, y equals 2x minus 8, I think. But you don't have to put it into slope-intercept form. This is a line nonetheless. And we have 6x minus 3y equals 4a. And we want these to be exactly the same line. Well, we know that this is just 3 times this. And so we know that we want this to be 3 times this if it's going to be the exact same line, right? Because if this was, let's say, if this 4a is 3 times 8, then this whole thing is the exact same line. It's just multiplied by 3. So we want 4a to be equal to 24, 3 times 8. Well, 4a equals 24, c equals 6. I want to make sure that makes sense to everyone. So just drop in the chat how you feel about this question, if that made sense. Because there's a bit of thought there of going from this is a multiple of this to going now then we need this 4a to be 3 times 8. So just drop in the chat. If you have any questions about that, I'm going to wait a few seconds, let y'all drop that there. Otherwise, we can move right along. All right. If you guys have any questions about it, feel free to drop in the chat. Otherwise, let's go on to problem 4. Sales for a business were $3 million more the second year than the first, and sales for the third year were double the sales for the second year. If the sales for the third year were $38 million, what were sales in the first year? It's a bit of a recursive action happening here. 60 seconds on the clock. Okay, so let's go over this problem, and then we will talk through the arithmetic sequence question. Okay, so this is kind of a bit of a mouthful of a question, right? It's heavy. But if we just kind of work backwards from what we know, it's pretty approachable. So sales for the third year were double the sales for the second year. That means 30, let's just use in millions, 38 is double the second year. Well, what number is 38 double of? 17, or no, 19. This is why you don't do mental math in the ACT. 19, right? That means there were $19 million in sales in the second year. Because if it doubled from the second to the third, and it was 38, it had to be 19 before. Next, sales were $3 million more in the second year than they were the first. That means if we had 19 million in the second, we had 16 million in the first. So it's kind of working backwards there to solve that problem. Otherwise, it's a pretty simple algebra problem, actually. As long as you kind of write it out and are deliberate in your actions, it's a pretty approachable question. So something just to keep in mind on a question like this, that's a word, like a kind of a mouthful, is really think through kind of what the question's asking and then go from there, right? Because a lot of the time these kind of word mouthful questions, there are only a handful of pieces that are really important. And that is $3 million more the second year than the first, double the sales of the second year, $38 million. Boom, answer, right? So don't get freaked out when you see like a giant question like this. Okay, so let's go back over, someone asked if we could go back over the arithmetic sequence question, right? So to recall, kind of let's back up a little bit, right? Let's get rid of these 1, 2, 3, 4, 5, and get rid of these 6, 7, 8, 9, and kind of move these out of the way. Let's just talk about what an arithmetic sequence means outside of the context of the question, right? Because that's really necessary. So an arithmetic sequence is a sequence of numbers, let's say A, B, C, D, E, so on and so forth, such that we are adding the same amount to each one. So A to B, actually I'm going to draw this like this, A to B, we do a plus, let's call it X, right? We add just some number. We add the same number from B to C, right? Plus X. And again, and again, and again. We're just adding multiples of X, right? Yeah, let me check real quick if we have a trig question. It seems like people are actually just asking questions. Let's see, is there a trig question? There does not seem to be. So I'll find one quickly, and then we'll do that instead of the some other questions, because if that's what you're concerned with, I want to cater to you guys. Right, so we're going to add X each time. So yeah, arithmetic sequence, we're adding X each time, right? This is different from a geometric sequence where we're multiplying by X each time. But for now, in arithmetic sequence, we are adding by X each time. So let's suppose we started the sequence with some number X, right? And let's suppose this X up here is now, let's call it D, right? Just different names for the same thing. So this is going to be X plus D. This is going to be X plus D plus D, which is X plus 2D. This is going to be X plus 3D, X plus 4D, X plus 5D is 8. We know that term. X plus 6D or 7D. $8D and 9D. Right, so that's how we got there. But the problem is we don't know what this X is, so there's nothing we can do. Right. However, there's kind of a neat thing here, right? We know that there's an 8 and a 13. So we know that this right here is actually X plus 7D or just 8 plus D, right? Because we're adding D each time. So this is now 8 plus 2D. And this is 8 plus 3D. And this is 8 plus 4D. But we know it's 13. So we can solve for D. 8 plus 4D is 13. We do our algebra. And we get D is 5 over 4. Now, we can actually just work backwards. We can do, we could work backwards like that, starting at 8. But now that we know, actually we have to, yeah. So starting at 8, we can say this is x plus 4d or 8 minus d. And that's because we know that the jump from 8 minus d to 8 is d because of the way we've defined this geometric sequence. And so we can continue this all the way down. 8 minus 2d, 8 minus 3d, 8 minus 4d, and our x is 8 minus 5d. So that is how we kind of filled all those in. From here, the question was asking for the sum of the first 4 terms. So we take these 4 terms right here, right? And we're going to add them together. So 8 minus 5d plus 8 minus 4d plus 8 minus 3d plus 8 minus 2d. So we add up the 8s to get 32. We add up the d terms to get minus 14d. We know that d is 1.25. We plug in d, and we get 14.5. So that really all this boils down to is understanding that in an arithmetic sequence, you have a common difference between elements. And the reason we call this a common difference is because using this sequence right here, b minus a is x. By the definition, right? A common difference. C minus b, that's also x. We have a common difference between adjacent elements. That's the same reason why in a geometric sequence it's called a common ratio and not a common difference. So that's kind of how that question works. If you have any more questions on it or want me to explain it differently, let me know. But that's how I would solve this problem on the ACT. Okay, so I'm going to quickly find a geometry question. I'll do some triangle geometry to start us off. Let's see if I can find a very quick question. Sorry, I'm trying to find a question just out of nowhere. And unlike the SAT, ACT practice tests are quite tricky to find. There we go. This should be a fun one. Okay, so this is actually this is just what we asked for, right? Triangle geometry, lines, angles, the whole shebang. Let me just check the answer of this question quickly. If the answer is anywhere. Okay, good. I just wanted to look at the answer before so I knew if I was going on the right track with this question. Okay, so let's talk through this question, right? I'm actually solving this problem alongside you guys, right? I have not seen this question before. So you're going to get to see kind of what it's like to look through a question kind of with fresh eyes. So in isosceles trapezoid ABCD, so first of all, I like to mark up my questions so we know these two sides are congruent. AB is parallel to DC. All right, that's useful information. BDC measures 25 and BCA measures 35. What is the measure of DBC? So we want this guy right here. I'm just going to kind of mark that and give it a little star. All right, that's our target. So let's think. First of all, kind of what's our major game plan here? Well, my thought is our game plan is going to be to find this angle right here, because if we have this angle, we immediately know this angle, right? If I call this angle A, right there, we know that 35 plus A plus, let's call this angle X, just because it's kind of what we're looking for. 35 plus A, I'm going to tone down, there we go, plus X equals 180, because it's a triangle, right? This triangle right here. So there's kind of our game plan is going to be to find A so that we can immediately find X. So how do we find A? Well, let's think about what we know. We know these things are congruent. We know these lines are not perpendicular, parallel. There's a useful piece of information. These lines are parallel, right? What do we know about parallel lines and angles? Well, let me draw this over here. If I have two parallel lines and what we call a transversal, what do we know about these angles? Well, let's look at it through this question. This 35-degree angle right here Ooh, 1 second. Let me think through this again quickly. Because I realized something. Oh, okay. Hold on a second. Yes, I'm going to double check something quickly. Yeah, okay. Okay, perfect. Again, you're seeing me go through this in my head for the first time. So we know that this angle here, right, is equivalent to this angle here. No, sorry. This angle here and this angle here, right? That's kind of really useful, and that kind of applies all over. This pair of angles is congruent to this pair of angles. So if we can find this angle right here, we know this angle. And then if we know this angle, we know this angle, and then we know that angle, which helps us find A. So that's kind of a lot of like this angle, this angle, this angle. Let's do it, and you'll see how it works. So because this is a congruent or an isosceles trapezoid, we know that each non-parallel side must be equal, and the angles that capture these sides must be the same. So we know that this angle here is the same as this angle here. And so we know that this angle right there is 25. Easy peasy. We also know then that this angle is 25. Let me actually make sure that's decent thinking. I don't think we even need that. We don't need that angle. I'm being silly. We know this is 25 because these are congruent, right? The parallel lines is just going to be useful possibly later. Therefore, we know that this is going to be 130 degrees right there, right? 130, because this is 50 degrees right here, has to add to 180. So we know that A, actually, we're not going to need this at all. Sorry, I lied. 25 plus 25 is 50, minus 180 is 130. Therefore, we know A is 50 degrees right there. And so we know then that X, if we plug in 50 right here, this is going to be 85. I'm going to type this out actually. It's going to be 85 plus X equals 180, which implies that X equals 95 degrees. There we go. X is 95 degrees. And that is answer choice B. So actually, you kind of saw me get tripped up there for a second because there were a lot of properties I was considering. And really, you could have solved this 800 different ways, right? That's 25, so that's 25. And so now we can figure out what this angle is, what this angle is, right? You can solve for just about every angle here because these triangles are kind of all similar or congruent to each other. But what I realized is that there's actually a much simpler way of going about it. And that's just realizing, find this angle, find this angle. And then from here, we know these two angles form a line, which means they add to 180. And so 30 plus 50 is 180. And then we know these three form a triangle, and we've got X. So that's kind of this question. I'm going to let take 10 or 15 seconds, type out any questions you have. Happy to talk through this. Otherwise, we'll move back into the practice we have. Actually, I'm going to ask, we could do one of two things. We could do more practice questions for the remaining 15 minutes, or we could do kind of open Q&A. Up to you guys. Drop in the chat what you would prefer to do. Right? If you have questions, happy to talk. If you guys just want to do free-form practice, also perfectly all good. And if no one says anything, I'll just go back to practice. All right, so let's go back to practice. Okay, I'm actually going to skip this question because it's not a great one. There we go. Okay, so this is a probability question. George has 4 sets of socks and 4 sets of shoes. Oh, okay, actually, I'm going to skip this one because we didn't go over. There we go. The lead of a screw is the distance that one screw advances, okay, in a straight line when the screw is turned one complete turn. If a screw is 2.5 inches long and has a lead of 1/8 inch, how many complete turns will it take to get all the way into a piece of wood? So 1 minute. Give that one a try. Okay, so this is kind of actually kind of a dimensional analysis question here. I'm going to show the answer and then we'll go over it. Oops, the answer here is C. We know that we have 2.5 inches of screw and we move essentially in 1/8 increments. So we know that x times 1/8 is going to be 2.5. Right? Because we go 1/8, 1/8, 1/8, 1/8. How many times do we have to do 1/8 to get 2.5? So we're going to multiply by 8 on both sides to get x equals 8 times 2.5, which is 20. It's actually a pretty simple question when you think about it in terms of how does this connect to an algebra question. Right? It's kind of a weird, abstract kind of what am I even thinking about here? I'm not a carpenter, but it's actually just an algebra problem. Okay, so it seems like we have a few questions, so let's go over those instead of going over more practice. So first of all, someone was asking, can you give an example of a time when you can't multiply two matrices? And to that I say absolutely. So first, let's look at an example where we can. So you mentioned a 2x2 matrix. So let's say like 1, 1, 2, 3, right? Just for example, I'm going to just put little matrix bars around it. And then let's say we had a 2x3 matrix. 1, 3, 5, 2, 4, 6. You know, I came up with that on the spot. Two random matrices. You can ignore that point. All right. So why can we multiply this together? Right? Well, we can take this first row and dot it with this column, and it works out in terms of the number of elements, right? This 1 goes to this 1, this 1 goes to this 2. Then we do it with the other column, 1 to 3, 1 to 4. We do it again, 1 to 5, 1 to 6. It goes here, right? 2 to 1, 3 to 2. I'm not going to draw the lines, but you have a kind of what we call a pairwise relationship there, right? When you can't multiply matrices, that's when you have, for example, elements in this matrix that don't pair here. So for example, let's say we had, let me erase these right here. And now let me move this up a little bit. Let's say now we added a third row, and that's 9, 8, 7. Right? It's still a matrix, right? Like it's still a perfectly fine matrix, but we can't multiply it. And the reason, I'm just going to move these matrix bars down here now, is if we take this 1, 1 and we try multiplying it by this 1, 2, 9, well, we do 1 to 1, 1 to 2. I don't have anything here to do with this 9, so you can't multiply these matrices together, right? And if we write this out, we can see this is a 2. Oops. This is a 2 by 2 times a 3 by 3. These two numbers inside here don't match, and so we can't multiply. And that's because this 2 right here is the number of elements here, this first 3 is the number of elements here. So if we change this to a 2 by 3, like before, right, 2 rows, 3 columns, now we get 2 rows right there, or excuse me, 2 columns, right? So 2 elements in each row times 2 elements in each column. And so each row and each column have the same number of elements. So that's kind of where you can. You'll see this happen if you can't multiply matrices, right? You'll bump into a situation where you go like, I don't know what I'm doing here. And that's a sign that you can't multiply those matrices together. Sorry, I almost went into an explanation that involved like linear algebra that I've been doing this semester, but that's kind of the general idea. Okay, so I was looking for some Venn diagram questions, but I want to make sure this is kind of what you were thinking. Is this the type of question you were thinking about, like something like this? I just want to make sure I go over the right types of questions for you. I can delete this. So is this the type of question you're thinking about, or is it something else? Yeah, so let me find a law of signs question as well. Like subjects. I mean, so, okay, so let's go over this and then we'll look for a law of signs question if we have time. So when you say like subjects, all the Venn diagram shows is what are called sets, right? So this is the set A, this is the set B, this is set C. And so like these could be different like subjects, so like math, science, and history, and students that like each one, for example. When this is asking which of the following does not belong to A, U, B, this U, I'm going to go through this very quickly because it looks like there's some hype for law of signs. This U here means union. So union. The union of two sets is basically when you take these two Venn diagrams and combine them. So this, what I'm shading in here, is A union B, right? A combined with B, literally the union of these two sets. So which of the following does not belong to it? Well, looking at the answer choices were 23, 6, 4, and negative 11. 23 is the only element that does not belong to the union of these two sets. So I know that's very quick, but that's kind of the general idea behind Venn diagrams, is they show sets. We also have a cap B, right? That's called a cap. And so if we remove scribbles, this means right here, this means intersect, right? So intersect is quite literally the intersection of the two sets. So this area here, that is the intersection of those two sets. So if they ask you, for example, what is an element in A intersect B intersect C? Well, that's something that's in A and B and C. That's this area here. So, so that's kind of the big idea. Okay, let me see if I can find a quick law of signs question. Okay, here we go. So this is a question. The law of signs is quite rare on your exam, so don't freak out if you're not like a huge fan of it. It's so rare that a lot of the times, if you see an old question from the ACT or SAT, they will tell you what the law of signs is. So let's recall the law of signs says that for some triangle ABC, sine A over A equals the sine of B over B equals the sine of C over C. Right? The ratios of the sines of imperial angles, the lengths of the opposite sides are equal. That's all this means. So in this case, this is our, let me do this in text. This is our A, this is our B, that's our C. So what it's asking is, what is the length of BC? Well, using the law of signs, we know that the sine of angle A over A is equal to the sine of angle C over C. Right? And the reason I use C is because we're already told that length. So let's think about, first of all, what this angle is here. Well, 34 plus 41 plus A, angle A, is 180. So 34 plus 41, that's 75. Plus A equals 80. So that means A is a 105-degree angle. Meaning this isn't a right triangle. That's okay, but it's not a right triangle. So now we can label this with 105, like that. And now we can get using the law of sines. So the law of sines tells us the sine of 105 divided by A is equal to the sine of 34 divided by 25. Actually, so in this case, they have it all written in terms of these signs. So let's just solve directly for A. So it's kind of tricky when A is in the bottom, so I'm actually just going to flip it. So A over sine 105 is equal to 25 over sine 34, multiply by sine 105 on top bottom. Get A equals 25 sine 105 divided by sine 34. You can plug this into your calculator, you get a number, but the answer there, then, if we kind of compare to our answer choices, is answer choice B, 25 sine 105 over sine 34. In general, the law of sines is useful when you're dealing with the sines and sidelines of a triangle that is not a right triangle, because you can no longer go, oh, well, the sine of this is opposite over hypotenuse, because there is no hypotenuse. It's not a right triangle. So that's kind of a hint that you need to use the law of sines, is if you're asked for a length or an angle of a non-right triangle, the law of sines will come in handy. And if you just remember kind of this guy right here, it's almost like a general formula that you can use when dealing with triangles like this. It also applies to right triangles. It's just slightly less useful because you have things like the Pythagorean theorem and trig ratios. Okay, so it looks like we have 2 minutes left. So if anyone has any burning questions, I'm happy to talk and chill for the next 2 minutes. Otherwise, there isn't much time left to kind of go over a question substantively. So I'll let y'all have another 30 seconds to think through and kind of drop your last questions in the chat. Otherwise, we will wrap up for the night. We'll give you a few seconds. All right, so it looks like nobody has any more questions, so we will wrap up for tonight. Thank you guys so much for sticking through, for putting in the work. Best of luck to you guys on your exam on, I want to say Saturday. I think it's on Saturday. And yeah, thank you guys for showing up. And I hope you all have a great rest of your night and good luck on the exam.